In the last part, we have looked at grain boundaries and its role towards strengthening. In this part, we'll be looking at grain boundaries and how they can be modeled in terms of dislocations. So we know that this region between two grains is a region of mismatch and the bonds are broken over here. Now let's understand how we can represent these boundaries in terms of dislocations. So there are different models for explaining the grain boundary nature. So we have seen this image where we have differentiated grain boundaries in terms of low angle grain boundary, which has angle of misalignment or misorientation angle less than 15 degrees, and high angle grain boundaries, which has this angle of misalignment to be greater than 15 degrees. In some of the textbooks, you may find this also. Let me write it down here. So you can see that this angle, they write it as something like 10 to 15 degrees. So this depends on a material, but maximum limit for defining this low angle grain boundary is less than 15 degrees. We'll be seeing it why is that so. So there are two boundaries which are defined when we try to understand these grain boundaries in terms of dislocations. Those are pure tilt and pure twist. So let me explain it to you what is pure tilt and pure twist is. So let's say you have this grain which has one orientation, and let's say you have another grain which is, with respect to this grain, it is tilted. So when when there is no alignment, they will be straight square here, and now these are tilted. Let me draw it here. So initially, if there is no mismatch, they will be perfectly like this. Now when there is a tilt, so I tilted this grain in this way and I tilted this grain in this way. So I create a misorientation angle. I create a misorientation angle here, and this kind of boundaries which is formed. So this kind of boundaries which are formed are called as pure tilt boundaries. So they are tilted, these grains are tilted with respect to this axis. And now let's understand what is pure twist. Now let's say you have this grain, and what you do, you have another grain which is twisted in this way. So you have this another grain which is twisted in this way, and you can see that these boundaries which are formed between these two grains will be of pure twist. Let me explain that to you. Let me write it down here. So let's say you have initially you have grain 1 with this and another grain, let's say, over it in this way. Now what you do is that you twist this grain with respect to initial grain, and so you are twisting this grain in this fashion. So these are twist boundaries. So with this, let's understand how these tilt boundaries and twist boundaries are represented with respect to dislocations. So you can say that here this grain boundary which is formed between this, so this is a region between these grains, and we call this region as a grain boundary. So we can represent this boundary as an array of edge dislocations which are lying over each other. So this is pure tilt, and pure twist we'll be looking at it in our further slides. So let's focus on pure tilt grain boundaries, and I'm considering tilt boundaries and considering a dislocation model. So here it is a model for symmetric tilt. So we have seen that that both the grains were tilted equally. So we are considering a model for a symmetric tilt low angle grain model. So here you can see that you have these two grains. Let me mark here. So you have this grain 1 and grain 2, and the region between them, you can see that we have marked some dislocations here that are edge dislocations which are above each other, or the stack of these edge dislocations. So this dislocation can represent these grain boundaries. Those are low angle grain boundaries here. and this is a misorientation angle theta. And let's consider the distance between these two consecutive edge dislocations to be d. And let's consider the purchase vector to be p. And now what you can find is that if you consider this total angle, that becomes theta, and if you just consider half of the angle, because this is symmetric tilt, so this angle, let me mark it over here. So this angle here becomes theta by 2, and thus when we find out this sine theta by 2, it has to be do twice of it. So 2 sine theta by 2, that will be b upon d. So you have this complete b, and that can be found out using 2 sine theta by 2 is equal to b upon d. So just using a trigonometry, you find this relation. And now if you consider the theta to be very small, so you can write this sine theta by 2 is equal to theta by 2, and thus we can get theta is equal to b upon d. Or in other words, we can say that this b, which is a Burgess vector, which is much smaller than the spacing between these two dislocations, and thus theta will be much smaller, and you can write that theta is equal to or approximately equal to b upon d. So mind you, this is a low angle grain boundaries, and we have defined low angle grain boundaries as, let us remember that theta is less than 15 degrees. So you have this model for a symmetric tilt boundary using an array of edge dislocation or a stack of edge dislocations. Now what is an implication of this relation? You find that, so this is a dislocation spacing, which is d versus tilt angle, that is theta, that is angle of misalignment or misorientation angle. Now what you find that if I decrease this d spacing, so if I try to bring these dislocations together, what is exactly happening? So if I try to bring these dislocations together, the tilt angle is increasing. Or when I want a small misorientation, I can have this d to be large. So if I reduce this d, so let me write it down here. So if d decreases, theta increases, and thus if I go on reducing this d, the misorientation angle can increase, and that is what is written over here as theta increases, d decreases. And what will happen because of this dislocation, let us mark it over here. So these dislocations will try closer and closer, and if they come closer and closer, theta increases. So as this dislocation come closer and closer, what will happen? The core of this dislocation will start overlapping. Core overlapping. And that gives us the high energy configurations. And thus this model cannot be used for misorientation angles more than 15 degrees. So you find that if I put theta to be 15 degrees, this d is much smaller and the cores will start overlapping, and thus that is not possible to have this overlapping of cores, and thus this model to represent grain boundary using edge dislocation will not able to explain theta which is more than 15 degrees. So now let's look at this dislocation model for grain boundaries. So here we have plotted the energy of grain boundary, that is gamma, which is joules per meter square, and here there is a misorientation angle. And we have considered this 110 tilt boundaries in aluminum, and you can say that at the theta less than 15 degrees represents low angle grain boundaries, and theta more than 15 degrees represents higher angle grain boundaries. So these are all higher angle grain boundaries here. And you can see this kind of boundaries. So you can explain as misorientation angle increases, this gamma, that is grain boundary energy, increases. And you can see that it increases with theta, and our dislocation model, which represents boundaries as an array of dislocations, H dislocations, can explain this increase in energy of grain boundary with respect to theta. But as soon as we enter into high angle grain boundaries, you can see that the boundary energy is more or less constant. And for some of the boundaries, you get lower energies. These are the cusp in grain boundary energy with respect to misorientation angle. So these are called as special boundaries, which has lower energy configurations, for example twinning, etc. Now let's look at the schematic in general for this kind of material. So we have grain boundary energy. Let me write it over here. Grain boundary energy, which has, you can write it as millijoules per meter square. And this theta, which is a misorientation angle, let me mark over here. So it is in degrees. And this region, which is a low angle grain boundary, you can say that gamma, that is this grain boundary energy, is proportional to theta. And at higher angle grain boundaries, it more or less saturates to an energy that is gamma SV, that is a surface energy for that material. So this gamma is more or less proportional to gamma SV upon 3, where gamma SV is a surface energy. Let me write that down also. And this is how we can explain the low angle grain boundaries and high angle grain boundaries. So remember that we are considering the tilt boundaries, and we explain it using a stacking of an H dislocations. Now we have considered this twist boundaries, and they will be modeled using screw dislocations. So I will not be dealing with this here, and rather it becomes out of scope of our course. So this is to get introduced that we can model grain boundaries using dislocations. Now let's look at some important terms when I talk about dislocations. Those are statistically stored dislocations and geometrically necessary dislocations. So these two terms are required, or these two dislocations are required to explain a polycrystalline slip in a material. Now let's consider we have polycrystalline material and we have these 3 grains which has different orientation. So you have these boundaries here, and let's apply some stress. Let's try to deform this polycrystalline material. Now what will happen? That there will be a slip occurring on these grains based on their orientation or a Schmidt factor. We have seen this. And let's understand that the Schmidt factor for these 3 grains are different, and if they are independent to deform, how they will deform? If you consider just the Schmidt factor, so if they deform differently and there is an overlap of these grains, there can be creation of voids. So here, let me write it here. So here there is an overlap. Here there is an overlap, and here these are voids which are created. If we consider these grains to deform independently, independent of each other, and thus we have overlaps and voids which are created if we consider the deformation according to Schmidt's law. But in practice, what happens is, during plastic deformation, the strain is accommodated by shape change and there are no voids or overlaps. So mind you, let's say we are deforming a material before, like let's say we can consider before UTS, that is ultimate tensile strength of a material, So you find that there is a plastic deformation which is occurring, but there is no void or overlaps which has been created. That is, we observe it experimentally. Now this can be explained using statistically necessary dislocations or statistically stored dislocation and geometrically necessary dislocations. So we have this grains or polycrystalline material is deforming in this way. So you have an elongation in this direction, and you can see there is a compatibility, that is a geometrical compatibility between these two grains. Moreover, you can say that the deformation can be constant in this part. So you have deformation without having any voids or overlaps. So these kind of dislocations which causes a slip in a grain, or they form during the deformation, these kind of dislocations are called as statistically stored dislocations, and they form during deformation. So these are statistically stored dislocations. And now we can see that these grain boundaries can be represented or modeled using dislocations. Also, the geometrical compatibility between these two grains can be explained using some dislocations or structure of dislocations. Let's say like this. So you have compatibility that has maintained between these two grains using this kind of dislocations, and these dislocations are called as geometrically necessary dislocations. That is to correct overlaps and voids, and this explains how geometrical compatibility is maintained between two grains, two adjacent grains or neighboring grains. So we have these two terms, that is statistically stored dislocations. Remember that they always form during deformation. That is, means you are plastically deforming a material, you will get formation of statistically stored dislocations. And these dislocations which are necessary to maintain geometrical compatibility, that is to avoid this overlaps and voids, such kind of dislocations are called as GND or geometrically necessary dislocations. Thus, you can write the total dislocation density is equal to dislocation density that is related to statistically stored dislocations and dislocation density related to geometrically necessary dislocations. So in this part, we have seen how to model a grain boundary using H dislocations, and we have seen what are statistically stored dislocation and geometrically necessary dislocations. And with this, I will stop here.